really good. Good, good, good. All right, so let's look at this. So we have the square root of 63 x to the 10th, y to the 9th. Let's see if we can get this to move. Here it goes. So the first thing I do is look at that 63 and I go, not a perfect square. So maybe you can see right off the bat that 63 is 9 times 7. But if you can't, then do a factor tree. 63 breaks down to 3 times 21, which break down to 3 times 7. So you have the square root of 3 times 3 times 7 times x to the 10th times y to the 9th. So now if you take that 10 on the x to the 10th and divide it by 2, that gives you 5. So that means x to the 5th comes out. And then if you take the 9 on y to the 9th and divide it by 2, that's 4 with a remainder of 1. So that means that 4x to the 4th comes out and x stays in, or y, sorry. Y's. So this turns out to be the square root of 3 squared just as a 3, that's 7, has to stay underneath the radical. X to the 5th comes out, y to the 4th comes out, and y to the 1st stays under the radical. Square root of negative 128. Good, awesome. Okay, so for those of y'all that didn't do it real quick, let's talk about it. So pull out the I first. Then we've got the square root of 128, and if you divide 128 by 2, you get 64, which is a perfect square. So you have I times the square root of 64 times 2, and then you take the square root of 64, which is 8. So you have 8I times the square root of 2. Awesome, you guys. Nice. Okay, most of y'all got this. Very nice. Okay, so let's just go through it for a second. So 3 minus 5i squared is the same thing as 3 minus 5i times 3 minus 5i. Let's see, did anyone, no one did that. That was 9 plus 25i squared. Happy about that. So when we do the distributive property, this gives us 3 times 3 is 9, 3 times negative 5i, negative 15i, negative 5i times 3 is negative 15i, and negative 5i times negative 5i is plus 25i squared. So that simplifies to 9 minus 30i plus 25i squared. And we know that I squared is the same thing as negative 1. So now we have 9 minus 30i plus 25 times negative 1, which is 9 minus 30i minus 25, which would be negative 16 minus 30i. Don't you like the way I spelled multiplication? Multiplication. I wonder about myself. I used to win spelling bees, but no more. Ooh, all over the place here. And I do not know why I checked. I promise I wasn't smoking crack or anything, but I do not know where that negative 10i squared came from. I think I just meant to put negative 10i, which is the right answer. So I don't know what happened there. That negative 10i squared is not right, but negative 10i is right. Somehow both those answers got checked as right. So let's look at this. And the reason I wanted to emphasize that this is not multiplication is because a lot of times people see these parentheses and they automatically think, oh, I need to multiply, but you don't. If there's an addition or subtraction sign between the parentheses, that means you're adding and subtracting. So here we have 3 minus 5i minus 3 plus 5i, and there's an implied negative 1 right in front of that. So you distribute that negative 1, which gives you 3 minus 5i minus 3 minus 5i. The 3's will undo each other. They cancel each other out. And then negative 5i plus negative 5i is negative 10i. Simplify I to the 17. Okay, so remember what Matt said, if you take the 17 and divide it by 4, you would get 4 with a remainder 1. And so if it's a remainder 1, it's like an I to the first. If it's a remainder 2, it's like an I to the second. If it's a remainder 3, it's like an I to the third, and so forth. So another thing, it's kind of like modular arithmetic. It just keeps on repeating and repeating. So we know the square root of -1 is I squared is -1, I to the third is negative I to the fourth is 1, and then it repeats itself over and over again till finally you get to I to the 17th, which is I. But it's easier if you just take the 17 and divide it by 4, because you know I to the fourth is 1, and that's going to give you 4 with a remainder of 1. So that means that I to the 17th is the same thing as I to the first. And if you had I to the 18th, you divide by 4 and you get a remainder 2, and that would be the same thing as I to the second, which would be -1. So if you know those first, you know that everything has to be an I, a -1, a negative I, or a 1, then it's pretty easy to figure out what higher powers of I are.
Yeah, they used to teach modular arithmetic pretty early, but they don't teach it so much anymore.
Nuh-uh.
It used to be called, it's also called clockwork arithmetic, is what they also called it. Because it's like if you convert military time to standard time, that's basically what you're doing. If you tell someone like 2,300 hours, you're talking about 11 o'clock. Because if you divide by 12, you're going to have a remainder of 11.
And it's really fun. It's kind of, yeah, anyway, like.
Yeah, we use it quite a bit when we do proofs and stuff. Yeah.
Goes raw. Okay, so the next slides are the homework slides. So you for sure, if you haven't been writing anything down yet, you for sure need to write these down. So again, really good to know these perfect cubes. These are the ones that we use the most. Since I to the third is 1, in other words, 1 times 1 times 1 is 1, cube root of 1 is 1. And since 2 to the third is 8, 2 times 2 times 2 is 8. The cube root of 8 is 2. 3 to the third is 27. It's like saying 3 times 3 times 3 is 27. So that means the cube root of 27 is 3. 4 to the third is 64. So the cube root of 64 is 4. 5 to the third is 125. So the cube root of 125 is 5. And 6 to the third is 216. So the cube root of 216 is 6. It's also really important to know that you can take the cube root of a negative number. No, I just show you this. So whenever we're talking about, when we're talking about imaginary numbers, you're never going to have an imaginary number that's associated with a cube root, because if you take the cube root of -1, that would be the same thing as the cube root of -1 times -1 times -1, because -1 times -1 times -1 is -1. Because anytime you have odd numbers of negatives, it turns into a negative. And if you have an even number of negatives, it turns into a positive. So then if you have the cube root of -8, that would be the cube root of -2 times -2 times -2, which is -2. So the main thing to know is if you're taking the cube root of a negative, you come up with a real number, not an imaginary number. Okay. So if you know these perfect cubes, then you can take, like, if you know the cube root of, let's see, 64, if you know that that's 4, and so if you know the cube root of -64, you would say, okay, that's -4. So again, I would definitely write these cube roots down. And then at some point, if you don't have them memorized already, you should commit them to memory, because we use them all the time. And anytime you're asked to find a cube root, always start thinking about these small numbers. You're hardly ever going to have a really big cube root, because they get too big too fast. So always start thinking about these small numbers when you're talking about cube roots. So here's the first question on the homework. This was actually one of those on the chart I just put up, so hopefully that will help. Okay, good. So if you missed that one, you probably did not write down those perfect cubes. So I'm going to give you another chance to write them down if you didn't write them down already, because this is super important. The cube root of 1 is 1. The cube root of 8 is 2. The cube root of 27 is 3. Cube root of 64, 4. The cube root of 125 is 5. And the cube root of 216 is 6. Those are very important. And then the same thing goes for the negatives. Cube root of -1 is -1. The cube root of -8 is -2. Cube root of -27 is -3. Cube root of 64 is -4. Cube root of -125 is -5, and the cube root of -216 is -6. So if you would write those down, that will definitely help you in this section. And if you commit those to memory, it will help you even more. Yay. Excellent. Laura. Yay. Good job, guys. Okay, this actually is in this lesson, but it was also on the previous lesson. The square root of y to the 11th. And is take the 11 divided by 2 and see what happens. That should tell you how to do that. Okay, so the first thing to remember whenever you have a square root, the index is always an implied 2. There's like a little 2. There's a 2 here. It's not written, but it's implied. Because we use square roots so often, they just decided not to put it in there anymore. Every other root you have to put in there, but the 2 you don't. So whenever you have something like the square root of y to the 11th, take the 11 and divide it by 2, and that tells you that 5 to the 5th comes out from under the radical, and then whatever the remainder is stays under the radical. Another way you can look at it is like this: the square root of y to the 11th would be, but you wouldn't want to do this all the time. Y times 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 y. So that pair can come out, that pair can come out, that pair can come out, that pair can come out. This guy doesn't have a partner, so he has to stay in jail. So we have y to the 5th out, and the single y has to stay inside. Another thing, guys, if you're kind of a sloppy writer, this is not the time to be sloppy, because subscripts and superscripts really make a difference. So you have to be very careful where you put your numbers. Otherwise, it gets super confusing.
I saw a few people using X for multiplying still.
Yes, Do not use x for multiplying. And I've made comments on several of your that evidently nobody reads, because I've seen some of y'all continue to use x for multiplying.
Yeah, if I see it again, it's definitely getting more points off next time. Because it looks like there's multiple variables. I can't tell.
Yeah, we're past that now. So to take the cube root of a variable, we're following the same principle as taking the square root. So for example, to take the cube root of x to the 29th, we could do it like this. X times 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 x is 3, 6, 9, 15 times x times x times x times x. Y'all get the point. And then count all the 3 of a kind, and that's going to take forever. So we don't want to do that. So we're going to take the 29, divide it by 3 this time, whatever the index is, and that goes in there 7 times. And I mean 9 times, sorry. 9 times 3 is 27, and you have a remainder of 2. So that means that this comes out, and x to the 9th comes out, and an x to the 2nd stays underneath. So this time we're looking for perfect cubes to pull out. So whatever the quotient is, that's the variable, that's the exponent that comes out on the x, and whatever the remainder is, that's what stays under the radical. And then make sure you don't drop that 3, because a lot of people do. That has to stay in there. Okay, most of y'all got that good. So this time we're looking for cube roots. So one way you could do it, since this is so small of an exponent, this would be the same thing as the cube root of r times r times r times r times r. This time, to come out from under the radical, you have to have 3 of a kind. Anytime you have 3 of a kind, it comes out as a singleton. So this 3 of a kind comes out as the r, and then these guys have to stay underneath the radical as an r squared. And the easier way to do that is, especially if you're working with larger exponents, is just to take the exponent, divide it by 3. Whatever the quotient is, that's the exponent that comes out. And whatever the remainder is, that's the exponent that has to stay under the radical. And notice this is a fourth root. You're going to be using the same principle, only this time you're looking for 4 of a kind. Okay. So the fourth root of s to the 10th, if you were to expand this, it would be the fourth root of s times 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 s. And this time we're looking for 4 of a kind. Every time we have 4 of a kind, it comes out as a singleton. So this 4 of a kind will come out, and this 4 of a kind will come out, and that gives us an s squared on the outside. And then what we're left with is an s squared on the inside. Now, actually, we could simplify this even further, but we're not going to do that in this class. This would actually be the same thing as s squared times the square root of s, but don't worry about that right now. If you go further, you will need to do that. So the easy way to do it is to take 10 divided by 4, and that's 2 with a remainder of 2. So that tells you that x squared comes out, or s squared comes out, and s squared also has to stay underneath. And don't forget the index. That's called the index. That tells you what root you're taking. The only time you don't have to write an index is if you're talking about square root. This is a square root problem, so this is the same as night before last, or last night's homework. Okay. So it's a square root. So even though it's not written, it's like there's a 2 there. So if we were to expand this thing all the way out, it would be 5 times 5 times 5 times r 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 times r. And every time you have a pair of r's, it comes out as a singleton. So there's 1, 2, 3, 4, 5, 6 pairs. And here's a pair of 5, so it comes out as a single 5. So we have 5r to the 6 times the square root of what's left under is the 5 and the r. And there is, of course, an easier way to do that. So the variable part, I would just take 13 divided by 2, which is 6 remainder 1. So that means an r to the 6th comes out and an r to the 1st stays underneath. And then if you break down the 125 into its factors, or if you recognize that 125 is the same thing as 25 times 5, and you'd have a perfect square in there. So you can just do it that way. This is a cube root. So we'll be looking for perfect cubes. Good. Most of y'all got that. So I'm looking for perfect cubes, which means 3 of a kind. So if I use a prime factorization tree, 2 times 54 is 108, 2 times 27 is 54, 3 times 9 is 27, and 3 times 3 is 9. So that comes to be 3 times 3 times 3 times 2 times 2. X to the 5th is x times x times x times x times x. So anytime we have a triplet, it comes out as a singleton. So the 3 comes out, the x comes out, and we're left with a cube root of 4 and an x to the 2nd. Now we're looking for a 4th root, 4 of a kind. Well, those of you that did it, most of you did it right. That's good. So let's look at this. Fourth root of 48y to the 6th. So if we break down 48 into prime factors, 48 is 2 times 24. I keep on dividing by 2 until I can't divide by 2 anymore. And then I'll start dividing by 3 until I can't divide by 3 anymore. And then 5 till I can't divide by 5 anymore, etc. So this comes out to be 2 times 24, 2 times 12, 2 times 6, 2 times 3. So that means if you look at all these right here, 2 times 2 times 2 times 2 times 3, that would be what you're looking for, taking the fourth root of. And then y to the 6th breaks down into y multiplied by itself 6 times. And now you're looking at 4 of a kind. It will come out as a singleton. So 2 will come out, a y will come out, and we're left with a 3 and a y squared under the fourth root.
We didn't do anything over third roots in the notes. Or they didn't do anything over third roots.
Yeah, this is in the homework. Otherwise, I wouldn't have put it in here. I just wanted to make sure they saw it. There won't be a fourth root on the test either, but it's good to see it.
There's a sort of easy way to do fourth roots if it's an even fourth root. You can do square roots of square roots.
Yeah. All right, so we're rationalizing denominators, and in math, it's like it's against the law, at least in earlier math classes, to have a radical in the denominator. It really doesn't matter, and I think it's more of a consistency issue, because if you can imagine, there's so many different ways that you can write things. I think, this is my personal opinion, you might disagree with me, Matt. I think at some point, math teachers just said, we have to have one answer that everyone can get, that so we don't take 10 jillion years to grade all these papers. That's my personal opinion. So to rationalize a denominator, you look at the radical piece in the denominator and you multiply both the top and the bottom by that radical, because you do not want a radical in the denominator. Again, they'll come and take you to math jail if you do that. So when you multiply a radical times a radical, a square root times a square root, basically all that does is get rid of the radical, because now you have a radical 9, square root of 9, which is just 3, and then 7 root 3. So your final answer, 7 root 3 over 3, which really doesn't look any prettier to me than 7 divided by the square root of 3, is what we're looking for.
I think it might be a little prettier just if you were to like crunch it in your head, maybe. Because if we do 7 divided by like a root 3 is a radical. So it's easier to think about 7/3 of that weird number.
Yeah, maybe that's true.
Than to maybe think about like 7 divided by that weird number.
Yeah, perhaps that's true. Okay.
But if you get a radical and then like a prime, then you're done like simplifying that thing, basically. Yeah. And anytime you have a radical left under a prime, it's going to create an irrational number. They don't really tell you that, but those will be irrational numbers.
Remember, this says simplify completely.
There is some like old Plato work where he like Protagoras, where he talks about a square whose area is like, there's one that's area is like 1, there's one whose area is 4. So like, what about a square whose area is 3? And so like he kind of suggests the existence of irrational numbers before they were even kind of
started.
Probably thought he was a heretic, but
right.
It's usually the story.
I know, right?
But I think it's also a really good example of the Socratic method that he does in there when he goes through that example.
You know, in my whole career studying mathematics, I've never had a math history course, and I think it'd be so fascinating to take one.
I took it like twice as an undergrad.
You did?
As a grad. Yeah.
Cool. All right, so let's see what y'all missed. Okay, those of you that did the red, you just didn't reduce the fraction. So you really knew what you were doing here. You just didn't take it all the way down. You would have gotten most credit for that. So we're multiplying by root 6 over root 6, and that gives us 10 times the square root of 6 over 6. And then both 10 and 6 have a factor of 2 that you can divide out. So you wind up with 5 times the square root of 6 over 3. So just make sure you still look for common factors within the fraction. Now, I don't know if, going back to this, if there had been a plus sign between those, you couldn't do that. But because there's not a plus sign, this is totally multiplication and division, you can factor out a common factor. If you have a radical on a whole fraction, sometimes it's easier, not always, but sometimes it's easier to split it up into two separate fractions. So for example, if you have like the square root of 25 over 8, you could split that up into the square root of 25 over the square root of 8, because you know that the square root of 25 is just 5. And then the square root of 8, you could take a 2 out, and a 2 would be left under the radical. And then all you would do is multiply by the square root of 2 over the square root of 2. And remember, when you multiply a radical times a radical, it just gets rid of the radical basically, because the square root of 2 times the square root of 2 is the square root of 4, which is just 2. And then 2 times 2 is 4, and you're left with 5 root 2 in the numerator. So sometimes it's easier to split a fraction that's under a big radical into two separate radicals. Okay. Okay, so we have the square root of 4 squared over 27. I'm like, oh, I know what square root of 4 is. So I'm going to go ahead and break this apart, because that's what I always do. If I see a perfect square, I like to break it up. So the square root of 4 over 27 is the same thing as the square root of 4 over the square root of 27. Square root of 4 is just 2. And the square root of 27 is the same thing as the square root of 3 times 3 times 3. So a 3 comes out and a 3 has to stay under the radical. And then you just multiply the numerator and the denominator by the radical part of the denominator. So we wind up with 2 root 3 over, and anytime you multiply radical by itself, another radical 3, that just undoes the radical because it'd be the same thing as the square root of 9, which is 3. And then 3 times 3 is 9. Let's see. 2 root 3 over 3. Yeah, so just be careful. Ten divided by the square root of 5x, and that x is also under the radical. And again, remember to simplify completely. Yay, most of y'all got that right. Excellent. Okay, so we're multiplying by the square root of 5x divided by the square root of 5x, because you always multiply the numerator and the denominator by the radical piece. And so that's going to give us 10 times the square root of 5x over 5x, because when you multiply a radical times itself, that gets rid of the radical piece. And then the 10 and 5 both have a common factor of 5, so you wind up with 2 root 5x. This one was the last one. It was really easy. Or the last one on this section. Great. You just multiply the numerator to the denominator by root 7, and that's what you get. Only one person didn't answer that one. Okay. So, okay, so if you pick the blue, you would be put in math jail because you can't have a radical left in the bottom. So if you had the 2 root 2 over 3 root 5, you're halfway there, but you still have to get rid of that radical in the bottom. So you'd multiply the top and the bottom by the root 5, and that would give you 2 root 10, because root 2 times root 5 is root 10. And then root 5 times root 5 is just 5, and multiplied by 3 is 15. This is the last problem. Yay, good going, guys. Okay, so awesome. Okay, so we're through, and man, did I time it right or what? I'm so impressed with myself. So if you have questions, I will be here for office hours. Also, Matt tomorrow is going to be going over the test, so I would encourage you to look over your tests, so make sure you have questions for him. And then, of course, he'll answer any questions you have over any of the other stuff that we've been doing. So there won't technically be homework on tomorrow for over the weekend, so I would strongly encourage you to start looking at the review. We only have one new section to cover on Monday, and then we'll review on Tuesday, and the test will be on Wednesday. So
Yeah, look at that last problem on the test again. Like a lot of people missed that one. I don't think everyone missed it, if I'm being honest.
Everyone did?
Yeah, there's one person that got really close, and then they did something wrong that I know they knew better than. Everyone else tried to pick the points that weren't the thing that they were supposed to pick.
Okay.
But everyone got it wrong the same way, so I don't know.
At least they're consistent, right?
Yeah. So there's a point of confusion that needs to be addressed tomorrow, but we'll talk about it. But definitely look at that last problem. It was a booger.
Okay, well, y'all are free to go unless you have questions, and then please stay online, and I will be glad to answer anything. Bye, Hunter.